Recording is started. It is Tuesday, October 11th. Come back from a 3-day weekend. So last time I saw you guys, you saw one of these O'Neill cylinder type deals. So we're going to go over this as an example and then hit some physics that introduced you guys back on Friday. But trying to get some momentum for this class. But well, tomorrow you guys are not going to be in this class. Where are you guys going to be tomorrow? Cafeteria. That's right, because there's a PSAT going on in this classroom, and I'm going to proctor that. Okay. So I just gave you guys a bunch of pages before I started this recording. One of them is a nice thick piece of card stock. That's going to be involved with well, let's set you guys up with a fun creative assignment while you guys are sitting in the cafeteria tomorrow. Let me pause this recording, get this phone call. Pause. All right, recording is resumed. All right, so I also passed out to you guys a couple other pages. There's this page here, chapter 7 from your textbook. So these are the problems that I'm eventually going to go over in class with you guys. Let me go ahead and show you guys what I had marked for your assignment. Okay, so you guys want to like circle these problems? Okay, good. That's probably a good idea. Just to circle these problems, just to keep an eye on the prize, know what we're eventually headed towards. That's it. Okay. So some problems from chapter 6 and from chapter 7. Wait a minute. Yeah. Okay. All right. Forgot how this printed up. The side that's not labeled is from chapter 6. And the side that says chapter 7, that's chapter 7. Okay, so that's how we're doing this. That's it. Right. And this is the, I'm pretty sure that I'll have gone over these problems with you guys by this date. But yeah, try and do that. Okay, so you guys got those problems? Almost. Okay. Anyway, while you guys are getting those down, the third page I passed out to you guys looks like this, and this is going to involve a kinematic connectivity that we're going to do in class today, which is pretty much just going to be extra notes for you guys. Okay. Extra special page in your notes. I gotta get it. It's really. Oh. All right, I think we're ready to go now. All right, so that over here. As always, I'm recording this and I'll post this to Google Classroom so you can catch this later too. All right. Yeah, let me set you guys up with what you're doing with that cardstock piece of paper. Okay. And I've also O'Neill cylinder. So I introduced this idea to you guys back on Friday. You guys remember this? I played you guys some videos, some artist renditions. Okay. Remind you guys how this works. So if you're out in the middle of deep space, right, there's no real gravity around, okay? But you can simulate a gravitational environment just by having a rotating cylinder. So here's this giant cylinder. Here's this axis of rotation. Okay? Suppose it's rotating at some angular velocity called omega. Okay? And oh, look at all these inhabitants here. Right? Now, you guys know that Newton's first law of motion says everything only ever wants to move in straight lines. So if this thing is rotating, right, and all these people are like fixed to the ground, right, then if you suddenly drop the walls away, just this whole thing just like fell apart, right, then if this thing is rotating, you know that each one of these individuals is just going to fly off tangent to their motion, right? Okay. Not straight away. No. They're going to fly off like tangent to the motion according to Newton's first law of motion. Okay? But if you put the walls back in place, they can't go that direction because the wall is like holding them in place. It's providing a normal force that's holding them in, right? And oh yeah, go ahead.
So what happens if like somebody's just floating in space and the wheel starts moving again? Will they get shoved to the wall?
Okay. Well, there's gotta be like a frictional force initially to drag them along, right? Yeah. If you're just like floating along and then this thing's rotating, it's like bam. Yeah, it'd be a transition period to get them in motion with it. But if you are along for the ride, then once you're moving along with this thing, yeah, there's a normal force from the wall that's holding you in. It's providing what's called a centripetal force. And if this thing is big enough and you're blindfolded, it might be really, really hard to distinguish the difference between this fake gravity and like true gravity, right? Now, if it's too small, then there's gonna be enough of a Coriolis effect. It's gonna be all weird and wonky. But if it's big enough, right? Right. So, I got some numbers up here to solve a problem, which we're gonna do. But before I get to that, right, let's here, I'm gonna flip my screen over. Or no, before I flip my screen, okay, here's what we're doing with this page. Okay. Right. So on this page, mark off a margin on the right side, about 2-3 centimeters, about 1 inch. The distance doesn't have to be exact. You just take a ruler and go zip. Right. So you have a line, right, on the margin on the right side. Okay. Right. So you guys are holding this paper. It's guys, is this a portrait or landscape? That'll be portrait. That's landscape, right? So you guys got the paper in front of you, landscape, right? Okay. Landscape. Put a margin on the right side. Zip. Okay. Okay. And what I'm going to have you guys do individually is to create a part of an O'Neill cylinder habitat, and then we're going to put these all together into one giant space colony. Okay, so like flip my screen over, show you guys some examples, and then I'll flip back and show you guys the rest of what we're doing here. All right, so okay. Find this video I've got. Right. This video of this all put together so you guys can see the final where it's all coming together. Okay, this might look like. And so I've always done this project with my classes every year. Okay, so hey, look at that. That looks like a big old O'Neill cylinder, doesn't it? Right, it's got all kind of fancy stuff on it. Right. And then hey, you have one panel in front of you. Right, so we're gonna like put all these panels together. Right. And so I think that's not the fanciest example that I've ever shown, but yeah. Gets the job done right there, right? And then here's some pretty good examples of panels from the past, right? So this could be one student's panel. Okay, here's one student's panel, right? So tomorrow's like a use your imagination type day. It's like, what do I want on my part of the space colony? Right? What are some things that'd be good to have? And maybe everything you need on Earth, right? How are you going to eat, drink clean water, get energy, right? You might think, if this thing's floating out in space, it might be kind of hard to import, export materials. So maybe you have to be careful about how you use space, right? But yeah, use your imagination, come up with something cool. Okay. I'll put the screen back over here. All right. All right, so just in case you still aren't quite sure how it's coming together, this page in front of you right now with that margin on the right side, okay, this could be like your page as a margin. And then here's classmates' pages. Right, they all have margins on the right side. And see how they're going to glue together like the back of this one, the front of this one. Glue, glue. If you glue them together like that, you can make like one giant strip. Right, with all these different panels. You guys get that? Then you take that strip, wrap it around into a ring. Hang it from a ceiling, and there you go. That'll be the Costa O'Neill cylinder. Okay, check that. There we go. Okay, any questions on how that's working tomorrow? Okay, so you guys gonna be where tomorrow? Yeah, cafeteria. Okay, and then you have this page. You just pull this out and use your imaginations and come up with something really cool. All right. So, questions so far? And so speaking of a new cylinder, let's go ahead and answer this question. I get through you guys a really similar question back on Friday. So if you had your notes out, you might be able to beat me to the answer even. Okay. So suppose these people are on an O'Neill cylinder with that's this size, has a radius of 500 meters. Or you might be pitched, it might be given to you, has a diameter of 1 kilometer. That would be the same idea, wouldn't it? 1 kilometer diameter, that's 1,000 meters diameter. It'd be 500 meters radius. That way it gave you radius because all the formulas are like that, right? And then suppose you want this to be spinning, so rotating, some angular velocity, so that there's a target artificial gravity of 9.8 meters per second squared. So all these people think they're on Earth, right? Okay. Maybe it's like a pair of questions, right? First of all, how fast does it have to rotate? And then the follow-up question could be this one here. How much time would it take to go around once? Okay. So some stuff that you guys saw back on Friday, remind you guys about this. So this rotating disc, and so many guys have some of these on your desk. I put out as many as I could find. Right. Remember, I'm looking at these three Roosevelts. And these three Roosevelts have all different linear velocities. If I point a radar gun, this guy's obviously going 0 meters per second. And then the further out it goes, looks like faster, faster. But they're all on the same rotating disk. So they all have the same turns per time. That means they all have the same angular velocity, which I've been calling omega, that curly looking W type character. Okay. And the connection between those is between linear velocity and angular velocity is you can just multiply by the radial distance from the center. That's what I want to write right at the center was 0 radial distance from the center at 0 linear velocity. It was spinning, right? Right, got that? You could also come up with these other kinematic connections from rotational motion to linear motion. So you guys remember, like the top example. Guys, what's the formula for circumference of a circle? Circumference equals 2 pi r, right? And remember how that's actually a specific example of this more general formula. So in general, how far have you gone distance-wise? Well, how far have you turned around, right, times your radial distance from that point. And remember, this is always going to be in radians. You could measure in revolutions or degrees. Those are all different ways to measure theta. But radians is the best way to measure it because it naturally feeds into the equations, right? The units actually work out. So in case of circumference of a circle, that'd be exactly 1 trip around, which, guys, how many radians is 1 trip around? 2 pi. Yeah, 2 pi radians. So if you do 2 pi radians times radius, isn't that 2 pi r, which would correspond to exactly 1 circumference. I see that? Okay. So you got displacement, velocity, and acceleration, right? Okay. Now, side note here, nowhere on this page did I say anything about centripetal acceleration, right? These two A-type values, this A is linear acceleration, like meters per second squared, and this alpha is radians per second squared. That's an angular acceleration, which is just how, what's the rate change of this rotating, like speeding up or slowing down spinning. Okay? But remember, centripetal acceleration is like a center-seeking force, which might be provided by friction, okay? Like a frictional force. Okay? That's something entirely different than anything on this page. Okay. Right, so then we said, hey, remember those 3 kinematic formulas from way back in the day to connect all these kinematic values for linear motion? Well, if you just pop in their rotational equivalents, like instead of x for distance in meters, now you say theta and radians, how far is something turned, right? And you get 3 completely valid new kinematic equations. Okay. Then you could take, here's a last page I want to show you guys. There's those 3 posters up there on that wall. Okay, these are them. Boom, boom, boom. Okay. What is the force to keep something on a curved path? From your lab, you guys figured out it was mv squared over r. We had the PVC pipe and the Play-Doh canisters. You guys figured this out empirically, right? Now remember, centripetal force is never a force unto itself. It's always provided by one of the classic forces. It might be a tension in a string. It might be a normal force from a wall. In the case of O'Neill cylinder, that would be true, right? In the case of a satellite going around a planet, it might be the gravitational force on the planet. We haven't quite got there yet, but we're working our way towards there. And then if you take this top formula, which you guys figured out from your lab empirically, and combine it with this one right here, right, V equals omega r. Okay, take this V equals omega r, take omega r, substitute it into that V. Okay, and that's how you get this formula, which is centripetal force, but it's like on a rotating disk. Right? Well, that's where it's most useful, right? And O'Neill cylinder is a prime example of that. Okay. Next step. Guys, what if I take this one? Again, this is all in your notes back on Friday. And I divide both sides by the mass. Guys, what is force divided by mass? What does that represent? Acceleration. And that would be centripetal acceleration in this case, wouldn't it? And on the right side, would it just be omega squared r? Okay, and that's going to connect finally back to starting to tackle this problem. Let's start from that point of view. So far, here's what we got. Because centripetal force is mass times angular velocity squared times radius, centripetal acceleration is just plain omega squared times radius, radial distance. Okay, and what you'll notice is that we have 2 of those 3 values right here. Okay, I told you how big it was, and I told you the target acceleration. So we just pop those numbers in, okay, and solve for how fast it has to rotate to make all this come true, right? And so my target acceleration is 9.8 meters per second squared. Right? That's what everybody feels like if they throw on the blindfold. Oh. How fast does it have to rotate? This could be in radians per second, but we're getting there. Okay. Given a radial size of 500 meters. Temperature. Okay. You guys do a couple of algebra steps and solve for omega. Okay. Okay, so omega squared is 9.8 meters per second squared divided by 500 meters. And the other algebra step is to take the square root. Okay. Like that. All right, let's try this out. So square root of 9.88 on 500, looking at 0.14. All right. Now here's where, as the number on my screen shows 0.14, okay, but you guys know in physics, almost all variables have well, numbers with units attached to them, right? Okay. The exception might be like coefficient of friction, but guys, this is 0.14 what? Yeah, radians per second. Radians per second, right? Like the meters cancel, we got 1/2 squared being square rooted, right? Remember, there are different ways to quantify omega. You could do degrees per hour. Like, oh, I bet if you took the Earth's rotation of 1 revolution every 24 hours, you could divide that out. It could represent some omega, right? You could do RPM, revolutions per minute, right? But the reason here, radians and radians per second is like the best way to measure the angles and angular velocity is because that's what naturally falls out of the math, right? See, without any extra effort, right, it naturally comes out to radians per second. Okay. Okay. You guys get there? Okay. But if you guys want a little more context, I could say times 180 degrees divided by pi. This is not super relevant, but that's about 8 degrees per second, just in case you were curious. What does 8 degrees per second look like? Okay. Well, I know what 8 degrees is. That's not like 8 tick marks. Okay, if I do that every second, that's probably pretty close to 8 degrees per second. Do you guys think? About 8 degrees per second? All right. So here we are up in space. We're watching this thing rotate. We can see it rotating. It's rotating real slow. Right? 0.14 radians per second. We can just make it out. Okay. And there's one last question to seal this whole deal, which is, hey, if it is rotating this fast, how much time would it take to go around once? You guys think we can do it? So back on Friday, I solved this question with dimensional analysis. Today, I'll do a little bit different approach. You guys remember distance equals speed times time? Okay. Do you think I could, and now this is true as long as acceleration is 0 meters per second squared, right? So as long as it's not speeding up or slowing down, can I replace each of these with a rotational equivalent, come up with a completely valid new kinematic equation? Like theta equals omega times t. Okay. Which, by the way, just in case you wanted to see it, that is what this is, right? Okay. If acceleration 0, just that. Okay. Okay. And then I could say, well, I know how fast it's rotating. Guys, what number goes right here? Yeah, 0.14 radians per second. This is 0.14 radians per second. It's right there. Okay. The question is, how much time does it take to rotate once? So I bet we're trying to solve for this t, right? Solve for this t. Okay. And to rotate once, that's called 1 revolution. Mathematically, what number feeds in right there? 2 pi radians. Bam. You guys got that? You guys remember in the math, in the equations, always put radian. This would be 2 pi, wouldn't it? Okay. Isn't 2 pi radians equivalent to 1 revolution? So if you wanted to solve for the time for 1 revolution, plug in 2 pi for theta. Okay, is that okay? All right, so one algebra step. Divide the 0.14 down. So what is 2 pi? Here, I'll spell this out. 2 pi radians divided by 0.14 radians per second. Radians cancel, seconds flips back up on top. Looking at 44.9, maybe I'll round that up to about 45 seconds. Okay. So if you had a 1 kilometer diameter O'Neill cylinder, you would want it to rotate once every 45 seconds, so that if you're standing on the inside surface, you would feel like there was Earth gravity. Okay. All right, you guys go back. Okay, all right. All right. Did we do top scientists? Did we do this? All right. So anyway, if your name is on the list, you did really awesome on forces. So good job there. I think I told you guys before before I started recording too. Everything up to last weekend, I put back in your folder. So it's all back in your folders there, including that quiz. It's all there. All right. Questions so far? All right. So let's do this rotational kinematics activity. You guys have a page that looks like this? You guys have this page? Who does not have this page? Already got that page? Right. Now this is just extra notes for you guys, extra notes. But just follow along with me and yeah, put this on. Still all this rotational stuff. Great. All right, so let's go back to this turntable. I do have some extra turntables, they're just scattered around on the desk. So as many as I've got are out there. Someone's a blank desk here. Get your hands on these, then could be helpful. Okay, so maybe give this thing a spin and watch it slow to stop. I wonder what this motion looks like. Say like in terms of equations, in terms of graphs. Okay. So by the way, these equations printed real tiny here are just the same ones as we've done in the notes so far. Okay. Okay. So following these directions here, because look at this, I got this coin on this turntable, right? Some radial distance from the center. Okay. First thing it says to do is 3 revolutions at constant angular velocity. In fact, all these questions on the left tables, notice they're all angular values, right? We got theta, we got omega, there's an alpha here, right? So really the coin can be positioned anywhere. Right? It doesn't matter what its radial distance is, right? But later on, we're gonna have to measure how far is it from the center. And there's a bunch of linear type questions, right? So we'll save that for later. Okay, so 3 revolutions. Guys, 3 revolutions. How many radians is that equivalent to? How about 1 revolution? How many radians? 2 pi, right? So 3 revolutions is how many? 6 pi. 6 pi radians. Is that true? Okay, so that's where that comes from. Okay. So let's do that. I'm gonna give this thing a spin, or actually here, I'm gonna apply a constant force. Okay, so to overcome the friction. Okay, so let's go 1, 2, 3. Okay, and then just let it slow to stop. Right, you guys get 1, 2, 3, and slow to stop. Okay. All right, so let's go. How much time did that take? Now I'm just going to make up a number that's probably pretty close. Let's say it took like 5 seconds. Right, that's probably pretty close. Let's say 5.0. If they timed that, it took like 5 seconds to do that. Okay. Now, if you know how far it turned and how much time, can you guys calculate how fast it was rotating? That you could, right? Just like you guys know, velocity is displacement over time. I bet I can say angular velocity is angular displacement over time. It's the same idea, right? Same format. So it went around 6 pi radians, and it took it 5 seconds to do that. Is that true? 6 pi over 5 at 3.77, maybe we'll round that to about 3.8 radians per second. Okay. So there you go. It was spinning about that fast. Okay. As long as I was keeping it in motion, a constant angular velocity is about 3.8 radians per second. Is that true? Okay. Let's go back. All right, then I take my hand off and I let it naturally slow to a stop. Okay. Let's go down here and hit the second box. Or hold on a minute. Never mind. There's something weird here. Let's say it took about 1.25 seconds to come to a stop. Right, so let's say you were timing that with a stopwatch, and that's what it came out to about. Okay. Something else I noticed is that, here, I'll show you guys what I did. Okay. So I went around 3 times, 1, 2, 3, and I took my hand off and went from here to right there and slowed to a stop right there. Right? Is that true? That's exactly what it did. Oh, now we can measure what is that angular displacement. Okay, how far did it? Oh, here we go. To go from here to here, like how far is that? And that looks like that's like 135 degrees, isn't that 135 degrees? Okay. Again, don't really care about degrees so much, but we can measure it in degrees and then convert that into radians, right? Okay. So because from here to here is 90 degrees. This whole thing's 180. And then this was about halfway between those two. Okay, so 135 degrees. Okay. So 135 degrees, how many radians would that be? What's that? 0.75. Yeah, three quarters of a pi radians. That's another way to think of it too, right? Yeah, so here. Let's think about this from a couple of points of view, okay? Because you guys know it's 2 pi radians all the way around, right? Or pi radians is half a turn. Okay, that's pi radians. If it was right here, isn't this like 3/4 of pi? Is that 3/4 of pi? Okay. So what's 3/4 of pi? Right, that's 2.36 radians. So 3/4 of pi radians is about 2.36 radians. Okay. Or so just from a different point of view, we should get the same thing no matter how we approach this. I said that was 135 degrees. We're looking at this angle right here, right? That's angle theta. 135 degrees. And you can convert, you could either say there's 180 to pi or 360 to 2 pi, however you do it. Okay. 360 degrees is the same thing as 2 pi radians. Again, if you want to simplify that a bit, you could do pi over 180. It's the same idea. Right. I should get the exact same number using this method, right? With the railroad tracks. Well, it's 135 times 2 pi on 360. It's the same thing. Still that number. All right. There we go. So from 2 different points of view, no matter how you look at it, this thing rotated 2.36 radians. Right? Okay. Let's just follow up slowing to a stop. Okay. But let's skip this box and we'll come back to that later. But the very last one, see where it says alpha radians per second squared? And I did throw in a negative sign just as a hint that, I mean, it would be negative, but it's like slowing down, right? So if it was going counterclockwise, which is the positive direction, then it slows to a stop. Okay. Well, I bet we could just break out those kinematic equations. Like, you have your choice of kinematic equations, but they should all lead to the same idea. What if I do omega final equals omega initial plus alpha times t, for example, right? This looks like VF equals V naught plus AT from way back in the day. Okay. And because if it slows to a stop, what's this number? Slows to a stop. Yeah, 0. 0 radians per second. Okay. And how fast was this thing rotating before I took my hand off? 3.8 radians per second. Just feeds in right here. 3.8 radians per second. We're saying what was the rate that it was slowing down, which should naturally come out to be a negative number. Okay. And this whole thing took 1.25 seconds to slow to a stop. 1.25 seconds. Okay. And make it believe a little bit, but that's kind of what the number would work anyway. Okay. Is that right? So see, can I subtract over the 3.8 and then divide down the 1.25? Of course, all these numbers have units attached to them. So alpha is equal to negative 3.8 radians per second divided by 1.25 seconds. I'm looking at this many radians per second squared, right? That's the rate that it's slowing down. Okay. Maybe I'll round that to about negative 3.0 because it's real close, right? Okay, is that right? Okay. Who's got any questions so far? All right, guys doing good? Okay, now to remind you guys what this type of acceleration refers to, because there's different kinds of acceleration we're juggling. Okay? This is the rate that it's slowing down rotating, right? Which is not, it's not a linear acceleration, although it's related to that. We're going to do it later. It's going to be connected, right? But the whole disk itself is slowing down at some rate. Right? But you know what else this is not? This is not a centripetal acceleration. Remember, centripetal acceleration results from a centripetal force that's like pulling something into a curve. Right? This is not that. Right? This is just the rate that it's slowing down spinning. Okay. Right, is that right? All right, let's go over here and hit these graphs. Now, you guys have two sets of graphs. There's rotational motion on the left, and there's linear motion on the right. Linear motion will, there's a reason for that. We'll get to that later. Okay. But the first one says theta versus t. So this is theta and radians versus time and seconds. The second one says omega and radians per second versus time and seconds. And third one says alpha, radians per second squared versus time in seconds. Okay, those two graphs. Okay. Now, can we take what we just did and map it onto these graphs? And each of these is going to be a two. There's two parts to the story. There's the part where it's going around at constant velocity, constant rotational velocity, right? And then I took my hand off and it slowed to a stop. And that point where it changes, I put a tick mark on the time axis. You guys see it? Okay. Can you guys imagine what each of these graphs would look like for that two-part story we just did before I draw it? Okay. In fact, if you guys can beat me to the answer, that's a really good sign that you guys know what's going on. If you draw with a pencil, you miss something, you can erase it. Let me do what I usually do with these type graphs. I'm going to start with the middle one, and then we'll branch out from there. Okay. So angular velocity versus time. Wasn't it just constant for those first three revolutions, okay, which was 3.8 radians per second? So I'm going to put right here, 3.8, that's radians per second. It's already embedded in the axis. Okay? And we're just doing that constant for the first, 5 seconds. Got 5 seconds right here, right? 5 seconds. Okay. And then I took my hand off, and then it slowed to a stop. And it took about 1.25 seconds to do that. I'm going to exaggerate this axis a little bit, so it's not going to be exactly to scale, but the shape is generally true, right? It'd come down to a stop right there. Right. Is that okay? And that would be at 6.25 seconds. Right? All good? All right, let's go hit theta versus t. So how far did it turn versus time? Angular displacement versus time. And at time 0, let's say it hadn't moved anywhere yet. So we got that point on the board, right? That point right there. Okay. Then during the first 5 seconds, first 3 revolutions, doesn't it pick up angular velocity at a constant rate? So what's that going to look like? I'm pausing. Yeah, straight line, right? I'm pausing to give you guys a chance to see if you guys can draw this with your pencil before I do, and it matches what I eventually show. Then it shows you guys know how to do this one. Okay. I mean, you would know yourselves. This is just extra notes for you guys. Okay. And then right at this moment, I took my hand off, and did it continue to rotate for a little bit more? Yeah, it slowed to a stop. But see, it was going counterclockwise for 3 revolutions. Then I took my hand off and it continued to go counterclockwise a little bit more, didn't it? Right. And if that's true, then was it still picking up angular displacement? Yeah. But just at a slower and slower rate. So there's more to this graph. What does the rest of this graph look like? You guys remember a car braking to a stop? It was still moving forward. but it was just slowing down while it was doing that. Remember that created like an upside down parabola type curve with a vertex right at the top right here? See that little hook? Right. So it's still gaining angular displacement, still going counterclockwise. It's just slower until it finally stops. This is an upside down parabola bit right here. Right? Straight line leading into an upside down parabola with a vertex right at the top. Okay, is that okay? All right, and then finally, how about angular acceleration versus time? So, yeah, if you guys beat me to the answer, that's a really good sign. Okay. So during the first 3 revolutions, it was just going at constant angular velocity, right? Guys, constant angular velocity, what do you think angular acceleration would be? 0, yeah, 0. So that's this whole interval of the graph, isn't it? Just 0, just like that. Okay, and then I take my hand off and it's slow to a stop. Slow to a stop. Oh, did we already calculate that that's -3 radians per second squared? It was losing 3 radians per second every passing second. Okay, so I'm gonna go here, go -3, and then that's boop, that right there. Okay. If you okay, so I'm showing a jump. In physics, jumps are okay. If you like, you could connect this if you wanted to, just make a really steep change. So you don't have to, but you could do something like that. Okay, you got two different values for acceleration. Boom, boom. Okay, that all right? You guys follow it? Sorry. All right. Okay, so let's also go back and fill in the cell that I skipped before. I said, what is omega average? Okay. Well, you guys, now let's say this is just for the part where it's slowing to a stop. So you guys see this little tiny triangle going on right here? Little tiny triangle. Right. So it was going this fast, 3.8 radians per second, and it slowed down to 0 radians per second. Do you guys think that the average of that was about 1.9 radians per second, just while it was slowing to a stop? That's what number goes right here, 1.9 radians per second. Okay, just starting the slowing down part. Okay. Okay. Now, why could that possibly be useful? Well, I'll show you guys why. Do you guys remember what the area under omega versus t represents? Guys, what is radians per second multiplied by seconds? That'd be radians, right? So do you guys think that the area of this little skinny triangle represents how far it turned while it was slowing to a stop? Let's try this out. What is 1/2 times base times height? Base of 1.25, height of 3.8. I'm looking at 2.38 about radians, 2.38. Or you could do 1.9 radians per second average times 1.25 seconds. And that's still the same thing. It's like 3.28. Okay. So you could do average velocity times time, or you could take the area under the triangle, and either way you get how far it turned while it's slowing to a stop. Okay, all right. All right, last part of this. Let's focus on one of these Roosevelts. It brings back up here. You guys can see the visual again. Okay. And let's focus on this guy on the very outside. I wonder how far away he is from the center. I'm looking at 14 centimeters. So I got 0, 7, and 14 centimeters. So 14 centimeters away. Back up on here. It's okay. 14 centimeters. Okay. So think about the motion again. What you just saw. So 3 revolutions followed by slow to stop. What was that guy's particular story in terms of linear motion? So I'm going to say he was at 14 centimeters away from the center. Okay, we're going to follow his story. How far did this guy go? Like, what distance did he run? Suppose that was like a racetrack and he was like running around. Okay. What distance did he go? Well, can you guys say that? Here, let me pull up the poster. Your linear distance is equal to your angular distance times your location from the center. Okay, you guys remember that, right? Just this one right here. So we got that. X equals theta times r. Well, what feeds into theta for just for the 3 revolutions? Yeah, 6 pi radians. Because 6 pi radians is 3 revolutions, isn't it? 6 pi radians. And isn't it 14 centimeters? Right. Maybe you could say centimeters per radius, the radius cancels out. Okay. What is 6 pi times 14? I'm looking at 264 centimeters. Woo! That is a pretty good distance. That's like over 2.5 meter sticks, isn't it? Right? I can believe that though, right? That turntable, right? Radius 14 centimeters, 3 trips around. Kind of booking it there. What speed was he going at? Notice I'm saying speed, not velocity. Oh, speaking of which, let me jump back to that last number. Guys, from beginning to end, for 3 revolutions exactly, what would you see his distance is 264 centimeters? Let me ask you a different question. What would his displacement be from beginning to end? 0. Right? Because he ends at exactly the same place he started, right? So displacement would be 0, but distance is 264 centimeters. Right. All right. Now let's go velocity. So I can do similar idea, right? I got 3.8 radians per second. Let's go V equals omega times R. Okay. So we've got 3.8 radians per second at 14 centimeters. I'm looking at 53 and change centimeters per second. I'm rounding a little bit, but 53 basically centimeters per second. Right here. Ooh, that's pretty fast too. That's like a half meter stick every second. All right, I can believe that though. Not crazy. What distance to come to a stop? Well, I see how far it turned to come to a stop. About to run to the bell, aren't we? Okay. Do you guys think you could? All right. Here, right before the bell rings, here's what I will tell you guys. These 3 linear graphs, X versus T, V versus T, A versus T, they have the exact same shape as the rotational ones. Okay, just different numbers and different units. But in terms of the shapes of these graphs, they have the exact same shapes. Let's go look like that. All right. So if you could just put on some numbers and some units, right? Again, this is just notes for you guys. And so I'm not going to see you guys tomorrow. Where are you guys going to go tomorrow? Cafeteria. All right, you guys gonna draw a really cool wheel cylinder panel there. All right, so you guys enjoy that, and I will see you guys the day after.